Here's the summative assessment on chemical reactions. Often these questions had two versions, so you've got one of them, and then the other one is a really good practice question if you're considering a retake. The first question here was kind of looking at the difference between a subscript and a coefficient. When I see A2, that little 2 means that there are two atoms of A that should be bonded together. When I see the big coefficient out in front of B or out in front of that compound AB, that just means that there are two of that particular particle. The big coefficients tell me the ratio of individual particles. The little subscripts tell me how many particles are chemically joined together. So if I look at my key, I want to pick the choice that has two atoms of A that are bonded together, and then two individual atoms of B. And then on the product side, I want two molecules of AB bonded together. Here were two questions where you were just filling in the coefficients. So in each there was an unknown transition metal, and they told us the charge. So part of the battle here is that I have to be able to write all these formulas correctly. So the first option, X is a transition metal with a +2 charge. X and phosphate would bond together. Phosphate has a charge of -3. So you can either crisscross or balance out the charge so that you get a neutral formula. You're going to need 3 atoms of X and 2 groups of phosphate. So you get a +6, -6. Sodium hydroxide, +1, -1. Sodium phosphate is one of my products. That's a +1, -3. So I need 3 sodium atoms. And then I'll have X2 hydroxide, which the Roman numeral just means that X's charge is +2. And then all we had to do was balance it. So you should end up with 3 atoms of X on both sides, 2 groups of phosphate. There's 6 sodium on both sides and 6 groups of hydroxide. The second one was real similar, but transition metal X had a charge of +3. The hydrogen sulfate is +1, -2. And remember that you'll have the chart of polyatomic ions for any test or quiz where you need it, or you can look it up in your book. So that's how I can get the formula and the charge of a group like sulfate. X3 hydroxide just means that X's charge is +3. Hydroxide is a -1, so I'll need 3 groups of hydroxide. On the product side, I make X3 sulfate, so X is +3, sulfate's -2, and water, which can also be written as hydrogen hydroxide. Obviously, writing it as H2O is totally fine as well. Now, what kind of happens here is that I'm going to end up with a total of 12 hydrogen on both sides. All right, so I've got on the reactant side 6 hydrogen coming from that hydrogen sulfate. And then I've got 6 hydrogen coming from that hydroxide group in the X hydroxide. There are 3 groups of hydroxide, each has 3 hydrogen, and then there are 2 of that whole molecule. So there's a total of 12 hydrogen on both sides. Then I should have 3 groups of sulfate on both sides, 2 atoms of X, and then there is sulfate, and the sulfate groups stay the same on both sides, but then I should also have 6 more oxygen. They're going to come from the hydroxide. Because again, there's 3 groups of hydroxide, and then there's 2 molecules, for a total of 6 extra oxygen that now end up in the water. Now you could also balance this by like putting a 6 out in front of like HOH. Hydrogen hydroxide is another way of writing water. Here we were looking at endothermic and exothermic. The first image shows sodium metal reacting with chlorine gas. A white solid of sodium chloride is left behind. But as I look at the picture representing that reaction, I also see energy being released. I see light, there's probably heat, I mean, maybe it's on fire. It's very exothermic. Often synthesis reactions release energy as you transfer electrons and form something that's more stable. More stable usually means lower energy. So I definitely have evidence that energy is released. That's exothermic. Energy is released when we form bonds. The opposite is true of breaking bonds. Electrolysis of water is a process in which an electric current is applied to a sample of water so that bubbles of hydrogen and oxygen are produced. We're decomposing the water into its elements. So in order to do that, we have to break the bonds. Breaking bonds requires energy. That's endothermic. Here, our energy source is the electric current. Sometimes it might be heat or light. We need some kind of an energy source in order to break bonds. This one wanted the model of a single replacement. So we want one single element reacting with a compound. And there should be two elements, or here are two little atoms that can switch spots. They replace each other. So in the second choice, I've got that gray atom being single. But on the product side, the gray atom was with the black atom, and the white atom is kicked out, and now the white atom is single. Here we were just identifying these reactions as different types of equations. The first reaction A should have been my double replacement. Double replacements will involve the reaction of two compounds, and you'll have two replacements. Two ions will switch spots. So it looks like hydrogen and iron switch spots. B is my single replacement, where there's a single element replacing an element in a compound. So it looks like zinc is replacing hydrogen. C is my decomposition. That's where I only have one reactant that splits apart to form little products. Now those little products might be here little compounds, or sometimes it might just be individual elements. D is the opposite. It's my synthesis. A synthesis will only have one product. So it could be little elements that join to make one product, or sometimes it's little compounds that join to make one big product. And then finally, E is my combustion. A combustion is something with carbon. We call it something organic that burns in oxygen, and the products are always carbon dioxide and water. Here we want to look at our reactivity series, which again would always be provided to you anytime you need it. We want to know which of these metals could be added to a solution of lead nitrate to produce lead metal. So I'm kind of thinking it as, there's some element, let's just call it X. It's going to react with lead to nitrate. All right, so I'm going to need two groups of nitrate to make that neutral, +2, -2, or crisscross the charges. Okay, so in order for this metal to chemically react and perform a single replacement, this metal X needs to be more reactive than the one it replaces. So which of these 1, 2, 3, 4, 5 metals is more reactive than lead? So I find lead. More reactive means that it's higher on the chart than lead. So nope, not copper. Copper is less reactive than lead, which means then that copper's got no business kicking lead out of this formula. But aluminum is higher, zinc is higher, magnesium is higher or more reactive than lead, but not silver. Silver is less reactive. So silver and copper would not result in a chemical reaction, but any of the others would. Kind of similar with the second option. You've got this unknown metal. We've got 5 to pick from, and it's going to react with zinc to chloride. Oh, kind of similar. I need 2 chlorine. So I want to know now which of these is more reactive than zinc. So I find my zinc, more reactive, not copper. That one's less reactive. Not iron, not lead. They're both less reactive than zinc. But this time I could either use aluminum or magnesium. And again, this chart would always be provided for you. You don't have to memorize it, you just have to know how to use it. The other chart that you'd always have available, besides obviously the polyatomics as well, is the solubility chart. This one helps with phase symbols. Is something aqueous? Is it a solid precipitate? I want to choose two reactants that can combine to form a precipitate of silver 1 chloride. And so here, if I think about it as a double replacement, look what happens if I mix silver 1 nitrate and sodium chloride. Oh, look at that. If I switch the like-charged ions, yeah, I would form a solution of sodium nitrate, which is fine. But then my other product is exactly what I want, silver chloride. Now, I had a few that were trying to do like some kind of a single replacement. So a couple times I saw something like this, where they were trying to take like silver plus the sodium chloride. And they were thinking, yeah, I mean, if we do a single replacement, I would result in the silver with the chloride. But if you look at the reactivity list, this wouldn't work. Silver is like the bottom of the reactivity list, and sodium is way up high. So silver is just not reactive enough to singly replace sodium. But as a double replacement, the only thing I have to worry about is that the two reactants would dissolve in water, which on this chart they would. Any salt with nitrate is soluble, and chlorides are soluble, with just a few exceptions. Sodium chloride will dissolve, but notice that silver is one of the exceptions. Well, yeah, because we were trying to form a precipitate of silver chloride, which means that it's a solid. And then at the end, we had a couple proposed balanced equations, and there's something wrong with them. And so we have to write a sentence explaining what is wrong and why it's wrong. So this could have just been a one sentence, or sometimes people wrote a little bit more. Both of these are very similar, like the error is similar. The error is in their final products formula. In the first red option, X represents an alkali metal, but alkali metals have a charge of +1. So if the alkali metal X is +1 and it bonds to oxygen, the formula should be X2O. And then I've got the proper balanced equation. Same kind of error with the blue example. Alkaline earth metals are +2. So if a +2 alkaline earth metal bonds with oxygen, you've got +2 -2. So their final formulas were both written incorrectly. And maybe the student was assuming that like X plus O2 forms XO2. Or maybe they just took the symbols of the reactants and kind of slapped them together. But what they didn't do is check the new charges, that whenever you combine two new ions, you have to check their charges. Just because it was O2 as an elemental diatomic gas doesn't mean that it's going to be O2 when it's in a compound. Then we have to see, well, what's oxygen bonding to? And what is the charge on that positive ion? In the next two, there was a single replacement. What is wrong and why is it wrong? In both cases, they replaced the wrong ions. Maybe the student was assuming that you always just take your single element and replace the first ion in the compound. but it's got to be like charges that can switch. So when my first element ends up being something that would form a negative ion, it's got to replace the negative ion in the compound. So bromine would replace iodine, and then chlorine would replace bromine. It's got to be like charges that can switch. Similar error with these two. They're both single replacements, and they did the replacement correctly. The magnesium is positive. It can switch with positive aluminum. Aluminum is positive. It can switch with positive copper. But I think, again, they had an error in one of their final product formulas. Just because you had 3 nitrate when nitrate was bonded to aluminum doesn't necessarily mean that you're going to have 3 nitrate if nitrate is bonded to magnesium. Again, when I make a new product, I join the ion. So yeah, magnesium is going to come in and bond with nitrate, kick out the aluminum. But then I need to write the proper formula of magnesium and nitrate. Since magnesium is only +2, I only need 2 groups of nitrate. And then I should rebalance the equation. Kind of the same issue in the blue example. Copper nitrate just needs 2 nitrate groups. But aluminum nitrate is +3 minus 2. So now I'm going to need 3 groups of nitrate. So moral of the story, whenever I make a new product, and I can do the replacement and switch the ion symbols, but I need to go and check the charges to make sure that I have the right formula for that new combination of ions. And finally, the last one. These were double replacements. They've got all of their charges written and the formulas written properly. The only thing they did wrong here was look up the wrong phase symbols on the product side. Right formulas, everything's balanced properly. But the last thing I kind of do with a double replacement is look to see the identity of my precipitate. The first one is supposed to form a blue precipitate in a colorless solution. But if I go look back on the solubility table, anything with an alkali metal like sodium is aqueous, and most chlorides are aqueous, but not silver, mercury, and lead. So the sodium chloride is for sure in solution, it's aqueous. But if I go back and look up something like copper hydroxide, most hydroxides are insoluble. That means they're solids. The only exceptions are things like alkali metals, which would maybe be like my sodium hydroxide. That should be the copper hydroxide. That's my insoluble precipitate. Kind of similar with the second example. Everything is right. The formulas are right. It's balanced properly. But anything with an alkali metal like potassium is soluble. And anything with nitrate is soluble. So potassium nitrate is the colorless solution, AQ, aqueous. The yellow precipitate is the lead chloride. Most chlorides are soluble. Like chlorides in the middle, soluble. Except compounds of silver or mercury or lead. Here are my 3 exceptions: silver chloride, mercury chloride, and lead chloride. And then that means my yellow precipitate, my insoluble product, should be the lead chloride.